Okay, we're going to build on our knowledge of electrochemical cells that we've learned so far. And in this lesson or this video, we're going to learn how to determine the voltage of different electrochemical cells. So before you even build an electrochemical cell, it's possible to know how many volts it will produce. And hopefully after this video, you'll be able to do that yourselves. A couple of things I want to have, make sure that you guys have out. Number one is your guided notes. Chapter 3 guided notes. Please have those out and be filling them in as we go through these slides. And also there's a paper that I passed out in class. The paper is called the Standard Reduction Potentials Table. This table is going to be so important as we go through this video. This table is located in your guided notes in your student workbook. But the one I pass out in class, it's nice to have a separate piece of paper so that you can have it next to you and look up those values as we need. So anyway, have those out and we'll get started. I want to start today with an analogy of water, okay, and how it relates to electrons. If you look at this picture here, it's showing a waterfall, and it says here that water only spontaneously flows in one direction. So the water spontaneously falls off of this waterfall. Spontaneously meaning that it happens on its own. Okay, we don't have to do anything. The water naturally just falls and downhill. Well, the same thing can be said of electrons. Electrons spontaneously flow in one way in a redox reaction. They always flow from higher to lower potential energy. And so if you look at an electrochemical cell like is shown over here, electrons will always flow toward the cathode. So the anode has a higher potential energy and it flows toward the lower potential energy. If we look at this slide here, it says the greater potential difference between the two electrodes, the greater the voltage of the cell. So if we're relating it to that waterfall, the higher the waterfall, or so to speak in this situation, the more the bigger potential energy difference between the cathode and the anode of your electrochemical cell, the more voltage you will produce. So we constructed this electrochemical cell in class, in lab last class period. So we used copper and zinc, and our electrochemical cell produced 1.1 volts. Well, you can use other materials. You don't always have to use copper or zinc. You could use other metals, and we might get different voltages here. And that's kind of the point of this video, is to teach you how to determine the voltage or the potential energy difference from the cathode to the anode. Okay, so let's start here with our notes. You're supposed to write down the definition of this term, electromotive force. It's abbreviated EMF, for electromotive force. It is the potential energy difference between the anode and the cathode in a cell. So it's the potential energy difference between the anode and the cathode in a cell, and that will determine our voltage. It's also called the cell potential. This is what I will be in class refer to it as the cell potential. And it's designated with this notation here. You've got a capital E for the potential energy, and then cell is written as a subscript. So this is the potential energy of the cell. Really what it's asking you for, the potential energy of the cell, is measured in volts. So the volt, abbreviated capital V, is the unit for electrical potential energy. So we're really going to be kind of focused on how many volts an electrochemical cell will produce. So we're interested in that electrical potential energy difference from the anode to the cathode. So the potential energy of the cell, this E naught of the cell, when you see this notation, you're going to see a lot in the coming days in the class. When you see this notation, the superscript, this little O right here, this is, chemists would say naught. So that when I look at this symbol, it's the E naught of the cell. That little zero, this little naught, tells us that the cell's voltage is calculated under standard conditions. So what are standard conditions for an electrochemical cell? Well, standard conditions are 1 molar concentration, so 1 molar, and under 1 atmosphere of pressure. So if you build your electrochemical cell and use solutions that are at 1 molar, and you're under 1 atmosphere of pressure, then then you've built one under standard conditions. And here's the deal: all electrodes are measured relative to the standard hydrogen electrode, which is given a value of 0 volts. So this is a picture down here of them measuring the standard hydrogen electrode. So they use hydrogen gas, and we just designate that value as 0 volts, and then we measure everything else. All other electrodes will be measured relative to the hydrogen electrode. So I've got, this might be the most important slide of this video here. This is called the standard reduction potential table. This is the paper that I was talking about earlier that I passed out in class. If you don't have one, make sure you come and get one from me. There's also a copy of this in your student workbook. But I wanted to spend a lot of time looking at this for a second. Okay? We just talked about at 0 volts, that's the standard hydrogen electrode. So we see hydrogen right here has 0 volts. Everything else is measured relative to that. And so you'll notice the cell potential measured in terms of volts right here. So this electrode would measure 2.87 volts relative to the hydrogen electrode. And there's a lot of different half reactions here. You're going to see the half reaction. This is a reduction half reaction. So all of these on this table are reduction potentials. So on your table that I gave you, I want you to kind of put a box around reduction. It doesn't report the oxidation half reaction, but there's a trick that we can use to get the oxidation half reaction from this table. So I want you to pay attention in the coming slides, and we'll show you how to do that. Okay, so please have this paper out as we go through the next few questions. So calculating the cell potential, how many volts does an electrochemical cell produce? We want to figure out the electric potential of the cell. The cell potential at standard conditions can be found through this equation. Please write down this equation in your guided notes. We're going to be using it for the rest of the chapter. So the E naught of the cell, or the electric potential of the cell, is equal to the electric potential of the reduction half of the electrochemical cell plus the electric potential of the oxidation half of our electrochemical cell. Okay, so here's that equation again. For the cell, the voltage of the cell, we just take the voltage of the reduction half and add that to the voltage of the oxidation half. All cell potentials are reported as reduction potentials. That's the table that I showed you. They're all reduction potentials. So how do you know which potential will be reduction potential and which one will be the oxidation potential? So here's that trick I was talking about earlier. This is very important. Okay, please pay attention to this part. You're going to look at your two electrodes, and the electrode with the largest reduction potential will remain positive and be the cathode. The other electrode, the one that's not as positive, will be your anode, and you will have to reverse its sign. So the one that's not as positive is going to be your anode, and you have to reverse the sign of the voltage in order for it to get an oxidation half. That might not make sense right now, but I promise you as we go through these questions, I'm going to refer to this rule a lot, so please stay with me as we go through these practice problems. Okay, so let's do a practice problem. Practice problem number 18 says, calculate the cell potential. Again, when it says cell potential, we want the E naught of the cell. We're going to use that equation. E naught of the cell is equal to E naught of the reduction half plus the E naught of the oxidation half. And remember, cell potential is really just volts. We measure it in terms of volts. So we want to figure out how many voltage, what voltage this electrochemical cell or battery will produce. So let's look at this. It gives us two half reactions for this electrochemical cell. It gives us the zinc plus 2 electrons goes to zinc. It gives us copper plus 2 electrons goes to copper. So I put a picture of the reduction potential table, and I know you can't see it on this video, but I still wanted to include it. I hope that you have this out right now, okay? Please have this out next to your guided notes as we go through these problems. Okay, so what you've got to do in order to figure out the voltage that will be produced by this electrochemical cell is figure out the voltage produced by each half reaction. So zinc plus 2, if you look, guys, zinc plus 2 is going to be right around here. And it's going to tell us that the voltage of zinc plus 2 going to zinc is negative 0.76. So I'm going to write that right here. Negative 0.76 volts. And this electrode, the copper electrode, let's find it on our table. So now be careful because it's plus 2. We have to find the one that's plus 2, and plus 2 electrons goes to copper. And so you're going to find it, let's see, right there, okay? And so it's positive 0.34 volts. Positive 0.34 volts. So I'm going to put that right here, 0.34 volts. Now that we found the potential of each half reaction, we're going to put and plug these values into our equation. To find the voltage of the cell, we're going to take the voltage of the reduction half and add that to the voltage of the oxidation half. But here's the problem. They are both written as reduction, because this is a reduction potential table. It doesn't give us oxidation values. So here's where we use that little trick. Whatever one is more positive is going to stay positive. That's going to be a reduction. So which one's more positive out of these two numbers? And the answer is this one. This is going to be a reduction. Half reaction. Your oxidation half is the other one, the one that's more negative. So this one's going to be our oxidation. Well, it's not given to us as an oxidation half, it's given to us as a reduction half because this is a reduction table. So what do? You have to flip the sign of this, and that will reverse this reaction right here. Moves that over here and this over here, but we have to reverse the sign. So this now becomes positive 0.76 volts. Okay. So when we plug that into this equation, our reduction voltage is 0.34. And we're going to add that to our oxidation voltage, but remember we need to change the sign so it becomes positive 0.76 volts. Okay, to find the voltage of the cell, we're going to add these two together. So the voltage, or the E naught of the cell, is equal to 1.1 volts. And that's my answer. Okay, and that's what the voltmeter that we have connected to our electrochemical cell shows, 1.1 volts. So that's pretty cool. I hope that you realize how useful this table is right here. We can figure out the voltage of an electrochemical cell or a battery before we even build it. And if we use different electrodes or different materials in our electrodes, different metals, we can figure out what the voltage will be before you even build it. So hopefully that makes sense. I know that some of this stuff is new, so we've got a few practice problems to try. Practice problem number 19 says find the electric potential of the cell, which just means voltage, of the cell shown below. Okay? But this one doesn't give us the half reactions. It does show us the electrochemical cell down here, but it still didn't tell us the half reaction, so we don't know which one's being oxidized and which one's being reduced. But hopefully you still remember how to do that, how to write half reactions. So let me help you through this one. We have to assign oxidation numbers. For aluminum, it's 0, it's a free element. NO3 is a polyatomic ion, its charge is a -1. But I've got 2 of them, so the total charge from the nitrate is a -2. That means the lead has to be +2. Okay, I'm going to erase that now. My oxygen's always -2. I've got 3 of them, so that's a -6. If it equals a -1, which is what nitrate equals, the nitrogen has to be +5. Okay. So let's continue on. The lead's oxidation number, a free element, is 0. Again, nitrate's -1, but I got 3 of them. And if each one is a -1 charge, the aluminum has to be +3, because this side's going to be -3, this side has to be +3. Okay, my oxygen's always a -2 times 3 is a -6. If it equals a -1, my nitrogen has to be +5 again. So give me a second to erase that. Erase these totals down here. We don't need them anymore. We are just interested in the oxidation numbers. Okay, now that we have the oxidation numbers assigned, we can figure out which one's being oxidized and which one's being reduced. Oxidation, you'll notice, goes up in oxidation number. So the one that's being oxidized is my aluminum. So I'm going to put ox right there. The one that's reduced goes down in oxidation number, so my lead here is being reduced. Okay? If I write the half reactions now, let's write the oxidation half first. We've got aluminum, and that's going to aluminum +3. To balance the charges, I'm going to need to add 3 electrons to this side. Okay, my reduction half reaction is going to be, we said was lead, so Pb +2. I'll leave a little space there, and it goes to Pb. In order to balance the charges, we need to add 2 electrons. Okay. So now that we know which is being oxidized and which one is being reduced, we come back to this table and we can figure out the voltage of this electrochemical cell. Let's start with the reduction half, because again, this is a reduction potential table. Let's find Pb +2 plus 2 electrons going to Pb on this table over here. So do we see it anywhere? Yeah, it's about right in the middle, underneath the hydrogen one. So it's right here. And if you look at its voltage, it's a minus 0.13 volts. Minus 0.13 volts. Okay, let's look at the oxidation half reaction, but remember, this table is a reduction table, so we're not going to see it written like this. To write it as a reduction, we're going to have to switch it, and it's going to go Al plus 3 electrons goes to Al. Now, can we find this one on the reduction table? Yes, so let's find that now. Aluminum plus 3 electrons goes to aluminum is down here. And it looks like its voltage is a negative 1.66 volts. So a negative 1.66 volts. Okay, now remember, when we're looking to find the electric potential of the cell, we have this equation. E naught of the cell is equal to the E naught of the reduction half reaction plus the electric potential of the oxidation half reaction. Well, our reduction was lead. The lead Pb plus 2 electrons going to Pb. that was our reduction. We're not going to change that one. This one's going to stay the same because that's our reduction. So we've got a negative 0.13 volts. And we are going to add the oxidation half reaction. Okay, but the oxidation half reaction was written as a reduction half. So how do we switch it to an oxidation half reaction? And the answer is we switch the sign. So instead of a minus 1.66 volts, we need to switch the sign because it was written as a reduction and we want it as an oxidation. So this is going to be plus 1.66 volts. Okay? If you do that, so 1.66 volts minus 0.13. So the electric potential of the cell is equal to 1.53 volts. And so that's how much voltage will be produced by this battery or this electrochemical cell. Okay, let's go to another one. Practice problem number 20. Again, you're supposed to find the voltage of the cell, the electric potential of the cell, but we have a different electrochemical cell. This time we're using this reaction. And again, I want you to find the E naught of the cell. So you're going to have to find the electric potential of the reduction half and add that to the electric potential of the oxidation half. You're going to have to go through and assign oxidation numbers first. Figure out which one's being oxidized, which one's being reduced. Draw your brackets. The reductions, you're going to look the values up over here. Remember to switch the one that's being oxidized, switch the sign, and add those together. I want you to try this one on your own. See if you can get it right. So please hit pause on your video right now and try it on your own. Once you have an answer, then hit play and see if you got it right. Okay, let's see how you did. Hopefully you were able to get an answer, but if not, let's see where you got hung up and see if we can't fix it. So Sn is tin. By itself, its oxidation number is 0. We've got silver nitrate here. Silver, if you remember, is always a +1 charge. But if you forgot that, that would be pretty easy to figure it out because nitrate's a -1, so the silver would have to be +1. Okay, if the nitrate's a -1, oxygen's always a -2, that's a -6. It's equal to a -1. So the nitrogen would have to be a +5. Okay. Silver just by itself is 0. Nitrate again, but we've got 2 of them. So we got a -2 charge total because each nitrate's a -1. So the tin would have to be +2, and because there's just one tin, that one is +2. Okay, my oxygen's always going to be a -2, but I've got 3 of them, so that's a -6. Nitrate's a -1, so the nitrogen has to be +5 again. Okay. So assigning oxidation number is an essential skill that hopefully you guys remember how to do. Okay, so let's go on and figure out which one is being oxidized and which one is being reduced. So if you look at this, which one is seeing its oxidation number go up? And the answer to that would be Sn, or tin, is being oxidized, because it's going from 0 to +2. Which one is seeing its oxidation number go down or be reduced? And the answer to that one is silver. Okay, that's our reduction. All right, so now let's write the half reactions. Okay, I always like to start with the oxidation half, and that is Sn, and that one goes to Sn +2. To balance the charges here, I'm going to add 2 electrons. You might be asking, why am I not including this NO3? Well, in our half reaction, the nitrate's really not contributing. It's not changing in terms of the redox chemistry here, so I'm just going to leave it off. It's really the tin that is being oxidized. Okay, so my reduction half. The one that was being reduced is silver, so I'm going to put Ag plus 1, and that goes to Ag. Just silver with a 0 as the oxidation number. But to balance the charges here, I'm going to add 1 electron. Okay. Now, to figure out the reduction potential of the reduction half, let's do that one first. So I'm going to look up on this table again. Ag plus 1 electron goes to Ag. And where do we see that at? It's near the top, or closer to the top, so it's right about here. And its voltage, the potential, is 0.8. So 0.8 volts. Okay, so I can actually just plug that in here, 0.8 volts. Now we need to figure out what the oxidation half reaction will be. But again, it's not going to be written like this because this is a reduction potential table. But it's easy to get it written that way. So let's just flip. Let's put the products as the reactants and the reactants as the products. So flip it over. Sn plus 2 electrons goes to Sn. So I hope you realize what I'm doing here. This is how it will show up on this table because it's a reduction table. So let's find that one. Sn plus 2 electrons goes to Sn. Okay, it's near the middle. So Sn plus 2 electrons. Yeah, I think it's right here. I know you can't see this, but on your table you should be able to find it pretty easily. And the voltage is a negative 0.14. Okay. But remember, the oxidation half, we have to flip the sign because this is a reduction table. So we have to flip that sign, so this becomes a positive 0.14 volts. So now we've got enough to answer the question. We can figure out the E naught of the cell, or the voltage of the whole cell, and that looks like it's going to be 0.94 volts. So if you constructed your electrochemical cell using a tin electrode and a silver electrode, you would produce an electrochemical cell with the electric potential energy, or the voltage, of 0.94 volts. Okay, hopefully you got that right. We're going to move on to a different concept now. And this concept is about spontaneity, or whether it is spontaneous reaction or a non-spontaneous reaction. For a reaction to occur spontaneously, now when I say spontaneously, I mean on its own, without help. The electric potential of the cell, or the cell voltage, has to be positive. So if the cell voltage is positive, it's going to happen on its own. All voltaic cells, or galvanic is another word for voltaic, all voltaic electrochemical cells are spontaneous. So all of them have a voltage, or an electric potential energy, of greater than 0 volts. Okay, well, let's contrast that to a non-spontaneous reaction. So non-spontaneous reactions do not occur on their own, but they can be forced to occur with the addition of energy. So when we add energy, we can make these reactions occur. They have an electric cell potential of values that are negative. So their voltage, when you figure them out, like we just learned how to do, their voltage would come out to be negative. So that's a non-spontaneous reaction. So non-spontaneous electrochemical cells are called electrolytic cells. So we had voltaic up here, they were spontaneous. Now we have electrolytic cells, and they are non-spontaneous. They require the addition of energy. And in the lab section of this class, we'll talk about and build an electrolytic cell, where we actually have to use a battery, some voltage, some input of energy, in order to get the reaction to occur. Okay, so let's do a practice problem on this idea of whether it's spontaneous or non-spontaneous. So it says to calculate the standard cell potential for each of the following reactions and tell which are spontaneous under standard state conditions. So if it's spontaneous, guys, it's going to have an electric cell potential of greater than 0. So it's going to be positive. Okay, so if the voltage is positive, it's going to be spontaneous. If it's negative, it's going to be non-spontaneous. So I think I have a couple of parts to this practice problem. Let's see. So I have 1 and 2. If I do the first one with you, I think you'll be able to see the process, and then I want you to do number 2 on your own. So let's go through number 1. First of all, I need to, in order to find the E naught of the cell, I'm going to write down that equation. The electric potential of the cell is equal to the electric potential of the reduction half reaction plus the voltage of the oxidation half reaction. So in order to determine that, I need to know which one's being reduced and which one's being oxidized. So let's assign oxidation numbers to this. Iron plus 2 is plus 2. Lead with a plus 2 charge is also a plus 2 oxidation number. Iron plus 3 is plus 3. And lead, as a free element, has no charge, is 0. So let's figure out which one's being oxidized, or seeing its oxidation number go up. And the answer to that is Fe, or iron. Which one is seeing its oxidation number go down or be reduced? And that would be the lead. So this one's our reduction. Okay, now let's write the half reactions. Okay, I always like to write the oxidation half first. So we've got an Fe plus 2, and that goes to Fe plus 3. And to balance the charges here, I'm going to have to add 1 electron. Okay, that was my oxidation half. My reduction half, it looks like lead was being reduced, so I'm going to start with Pb plus 2. I'm going to leave a little space there because I think I'm going to have to add an electron or 2. And that's going to go to Pb, just pure lead. Okay, and to balance the charges, I'm going to have to add 2 electrons right here. All right, so now what you got to do is look on the table, your reduction table that I gave you. I didn't have room to put it on this slide, but if you look at that table, I want you to find out where Pb plus 2 electrons goes to Pb. Okay, and look near the middle of that table, and you're going to find the voltage there was negative 0.13 volts. 0.13 volts. Now, the oxidation half's a little tricky, again, because your table is written as reduction. So what you're going to see on the table for this one is going to be Fe plus 3 plus 1 electron goes to Fe plus 2. And if you look up on that table, let's see where that one is. Fe plus, be careful, it's not Fe plus 3, it's Fe plus 2. Or no, Fe plus 3 plus 1 electron. So be careful not to mix that up. Oh, I don't see it. Okay, it's near the, it's about a quarter of the way down the page. So Fe plus 3 plus 1 electron goes to Fe plus 2, has a voltage of 0.77 volts. 0.77 volts. Okay, now be careful because that is a reduction potential, so we need to switch the sign so this now will become negative because we know that was our oxidation half. So when we plug it into this equation up here, my reduction comes from the reduction half reaction is a negative 0.13 volts. We're going to add that to the oxidation, which becomes negative 0.77 volts. And so 0.77, negative 0.77 minus 0.13 is a negative, so this is equal to a negative 0.13 9 volts. So if your voltage of the cell, or the electric potential of the cell, is equal to a negative voltage, is it going to be spontaneous or non-spontaneous? And the answer to that is non-spontaneous. So this first one here is non-spontaneous. This would be an example of an electrolytic. Cell. Electrolytic cell. It's non-spontaneous. It would never happen unless we gave it some energy and made it become spontaneous. So anyway, that's number 1. I want you to do number 2 exactly the same way and determine whether it's going to be a spontaneous reaction or a non-spontaneous reaction. So please hit pause on the video, try it first on your own and see if you can get an answer. Then hit play once you have your answer. Okay, let's see how you did. I'm going to quickly go through this one. Try to go quickly. Magnesium is a free element, so it's 0. Nickel is +2. Magnesium is +2 here. And nickel as a free element is 0. So if you draw your brackets, it looks like magnesium is being oxidized. And it looks like nickel is being reduced. So when you write your half reactions, I'm going to write my oxidation half first, so I'm going to have my magnesium, and it's going to magnesium +2. But to balance the charges, I'm going to have to add 2 electrons to that side. My reduction half reaction is going to be the Ni +2. I'm going to leave a little space because I'm going to have to add electrons there. And that goes to Ni. And to balance the charges, since this is 0 and this is +2, I need 2 electrons right there. Okay, so this is where you go to that table, the standard reduction potential table, and look up the voltages for each half reaction. So it looks like I always like to do the reduction half first, okay, because that's what this table is a reduction potential table. So let's find Ni +2. +2 electrons goes to Ni, and I see it about halfway down the page, and the E0 of the reduction is equal to negative 0.25 volts. Okay. Now let's do the oxidation half, but remember it's a little tricky because they write it as a reduction. So what you're going to see is the Mg +2 electrons go to Mg. Since I switched it, I have to switch the sign. So let's remember that. So magnesium +2, it's near the bottom of the page, almost near the bottom. So the voltage of that half reaction is a negative 2.37 volts. But remember, this is the reduction, and it wasn't the reduction half reaction, this was oxidized actually. So I'm going to switch the sign, that's going to become positive. So when you put it in this equation, E0 of the cell is equal to the E0 of the reduction plus the voltage of the oxidation. So my reduction was a negative 0.25 volts. Let's add that to the oxidation, which was 2.37. And so if you take 2.37 and subtract 0.25, the electric potential of this cell is equal to 2.12 volts. And it's positive. So if it's positive, that tells you that this electrochemical cell is spontaneous. So hopefully you were able to get that half, or this electrochemical cell in number 2 was spontaneous. Again, because it had a positive electric potential for that cell. If it has negative, like on number 1 it was negative, that tells you it's non-spontaneous. Okay, let's see if we got those right. I wrote over the top of it, but we got number 1 right. Looks like negative 0.9, and it was spontaneous. And number 2 was 2.11, and it was spontaneous. So yeah, we got it right. Okay, now there's one final topic in this video that I want to talk about, and it's called line notation. When we're dealing with electrochemical cells, you see line notation all the time. So you want to pay attention to this part, and let's make sure we get this part learned. So line notation, you're supposed to write in your guided notes what it is. It's a way to abbreviate the construction of an electrochemical cell. Here's an example of line notation. So we have zinc, line, zinc plus 2, 2 lines, copper plus 2, line, and then copper. So if we look at this example, it means something. It's a way to abbreviate the construction of an electrochemical cell. So what you're going to notice is that the anode material is listed first. This line separates the anode material from the anode solution. So this is going to be your anode solution, your electrolyte solution. The 2 line separates the half reactions. So this is 1/2 reaction, the anode half, and the 2 lines separate it from the cathode half. Okay, and then after the 2 lines you have your cathode solution. A line separates the cathode solution from the cathode material. So when I was learning this for the first time, I tried to make a way to remember it. And so it just goes in alphabetical order. You list the anode first. The 2 lines, then you're going to put the cathode. So A comes before C. That's kind of how I remembered it. And if it's got a charge here, guys, that's your anode solution. So you've got the anode material, this electrode, this is the metal, list it first, followed by a line. Then you've got your anode solution. It's going to have some charge, and it's going to be an aqueous or water solution. The 2 lines separates the anode half reaction from the cathode half reaction. Remember, the anode is your oxidation half reaction. So this is your oxidation half. Cathode is your reduction half. How do you remember that? If you remember from the previous video, we talked about a red cat. That means reduction happens at the cathode. So this is our reduction half reaction, and this is our oxidation half reaction. Okay, so knowing that line notation, let's look at a couple of electrochemical cells here. So an abbreviated representation of this electrochemical cell, if this is our anode and this half is our cathode, how would you write the line notation for this? So let's think about that. We've got the anode material. So what is our anode material? Well, it's zinc. So we're going to put zinc. 1 line separates the material from the solution. And we've got our anode solution is zinc. Sulfate's a -2, so the zinc here is going to be +2. Followed by 2 lines which separate the half reactions. So we go to the other side. We've got our cathode solution, SO4 has a -2 charge, so copper is going to have a +2 charge. Followed by a line which separates the solution from the actual electrode, the metal part's copper. And so that's what our line notation would be. It's much easier to write this than it is to draw the whole electrochemical cell. And so chemists oftentimes will just abbreviate that electrochemical cell by writing this line notation. It is pretty useful. Okay, so practice problem number 22. It says, what is the cell potential, the voltage, for the following voltaic cell? Okay, now pay attention. This is a voltaic cell, and it wants the cell potential. Well, we figured out in the previous practice problems how to find cell potential. And cell potential is given by this equation. We find the electric potential of the reduction half, the voltage of this reduction half reaction, and we add it to the voltage of the oxidation half. Well, okay, so this is our anode. So we have to pay attention. This first part is our anode, and this part is our cathode. So in order to determine what is being reduced and what is being oxidized, we've got to remember the red cat, which means reduction happens at the cathode. So this is the reduction half reaction. This is our oxidation half reaction. Once we know that, we can use our reduction potential table to figure out the voltage of each half reaction. So let's do that now. Let's do the reduction part first. If we wanted to write the half reaction, it would be this. Cu plus 2 electrons goes to Cu. If you look that up on the table, the E naught of the reduction, so the voltage of this reduction half reaction is going to be 0.34 volts. Okay? Our oxidation half reaction is going to be written like this. But you're going to notice that on our reduction potential table, this is not going to appear. So in order to find it, we need to write it as a reduction, so it's going to be Pb plus 2 electrons goes to Pb. But since I reversed it, now I've got to remember to reverse the sign. So let's find that one. And so this one has a E naught reduction of a negative 0.13 volts. But that's reduction. But we know it was the oxidation half reaction. So how do we find the oxidation? We switch the sign. And now it becomes the oxidation half reaction. So it's going to be positive 0.13. So if we want to figure out the cell potential, we plug it in here. Our reduction was 0.34 volts, right here. And we're going to add that to the oxidation of 0.13 volts. Okay? So it looks like it's going to be so the electric potential of the cell is equal to what does that come out to be? 47 volts. Okay, and so even if they give us the line notation, we can still figure out the potential of the cell. Okay, practice problem number 23. This is the last practice problem on this video, and I want to give you a chance to go through and figure this one out before I solve it for you. So it says a voltaic cell is constructed using electrodes based on the following half reactions. So it just gives us these half reactions here. It doesn't tell us which one is being oxidized, which one is the reduction, but it does tell us that it's a voltaic cell, which tells us that the E naught of the cell is positive. So the voltage better be positive. So we can arrange it so that the voltage is positive. Okay. Number one, it says which is the anode and which is the cathode in this cell? Well, that's a great question. If you remember red cat, reduction happens at the cathode. So we know that the cathode is going to be the side that is reduced, and the anode is going to be the side that is oxidized. So I'm going to put ox by anode and red by cathode. So how do we figure this out? We know that this is a voltaic cell, so the cell potential's got to be positive. I'm going to pause the video for a second, and I want you to look up the reduction potentials of both of these half reactions and figure out how it has to be so that the cell potential is positive. So hit pause on your video and try that and see what you get. When you have your answer, hit play. Okay, let's see how you did with this part. If I look up the Mg plus 2 electrons goes to Mg, it's near the bottom of your table, and the voltage for that is a negative 2.37 volts. Okay. And if I look up the copper plus 2 electrons goes to copper, I'm getting that this one is 0.34 volts. All right. So if it's got to have a positive electric potential for the cell, if it's got to be positive, it can only go one way. So because this is negative, I'm going to want to reverse the sign here. In order for this to be positive, I'm going to have to reverse the sign. Well, if I reverse the sign and it's written as a reduction right now, I want it to be the oxidation half reaction. So this one's going to be my oxidation half reaction, and I'm going to put 2.37, not minus 2.37. So we know that the anode is going to be the magnesium. Okay. And the cathode, I want this to remain that, so it's 0.34. So we know that the copper is going to be my cathode. If it was the other way around, guys, it would be a negative cell potential. And we know it's not negative because this is a voltaic cell, which is spontaneous. It has a positive voltage. Okay, number 2, what is the standard cell potential? Well, we figured that out basically, so we just have to finish this. So we're going to take 0.34 and add it to 2.37. So 2.37 plus 0.34. And that is so that sum is 2.71 volts. And number 3, it wants you to write the line notation for this electrochemical cell. Remember, there's a specific way to write the line notation. I would want you to put your answer down here, or on your guided notes, write in your answer. Let me give you a second. Please try that one and see if you can get the line notation correct. Okay, let's see how you did. Remember the line notation, it has to be the anode material first. So what was our anode? Well, it was the magnesium, and that was our material, was the Mg. So I'm going to put Mg, line. Now we need the anode solution. The anode solution is going to be in your aqueous part, the water part. It's going to have a charge here. So I'm going to put Mg plus 2. Now the 2 lines, that separates the half reactions. This was our oxidation half reactions, or the anode. And now we've got the reduction half reactions, or the cathode, over here. We need the solution listed first, and my solution was the copper 2+, so I'm going to put Cu plus 2. And my cathode material was the copper, so Cu. And that's how you would write the line notation for that electrochemical cell. So let's see if we got this right. So copper is the cathode, which is what we said. Copper was the cathode. Magnesium is the anode. So we did get that one right. Okay. Number 2, the potential of the cell, or the voltage of the cell, was 2.71 volts, and that's what we found. And let's see if we got this part right, and we did. The line notation was what we wrote. So there's a lot of stuff going on right there, guys. hopefully, as you watch the video, you were able to understand all of that. If not, you could watch the video again or come and talk to me and I can help you through some of this stuff. To give you some more practice, I've got a couple of worksheets in your student workbook to give you more practice with this stuff. It's the electrochemical cell worksheet number 1, and there's an electrochemical cell worksheet number 2, which after watching this video, you should know how to do both of them. So again, it's electrochemical cell worksheet number 1 and number 2. Please go to your student workbook and try those. And hopefully this video helped.